Hi, how is everybody? So welcome to chapter 12, part 3. So today we're going to look at colligative properties. And so colligative properties are properties of a solution that only depend on the number of solute molecules that are in that solution, not particularly what it is. And so if you think about a solution maybe where I add glucose, sugar to water, and a solution where I would add salt to water. If I were going to taste those solutions, they would taste very different, right? And I would think, okay, one is a sugar solution and one is a salt solution. In a colligative property, it doesn't matter that I added glucose or salt. A colligative property is a physical property that's going to be affected only by the number of particles, not the actual type of particles. So adding sugar and adding another sort of compound might have similar effects on the colligative properties, even though those solutes are very different. And so today we're going to explore these colligative properties and kind of dig into that and the effect that they have on solutions. And so here's our objectives for today. So we're going to be able to identify colligative properties, what they are, understand vapor pressure. So we're going to deal with one particular colligative property today, that's vapor pressure, and the effects that solutes have on vapor pressure. We're going to learn a new law, Raoult's law, and use it to predict the vapor pressure of a solution. And then we're also going to recognize the conditions under which that law is not predictive. So Raoult's law is not always predictive. So that's our goal for today. So like I said, a colligative property is something that only depends on the number of particles, not the type of particles. And when we get into part 4, so our next video, not today, we'll talk about electrolytes and non-electrolytes and the difference between those. Today we're just going to kind of orient you around vapor pressure, because vapor pressure is an important component of a solution. It's what's happening above the solution, but it's one that we don't really focus on too much because we're always focused on what's happening directly in that solution. Let's review really quickly some terminology. So if I have my states of matter, solid, liquid, gas, if I'm moving in between these, in particular, if I look from moving to a liquid to a gas, we would call this boiling or vaporization. So in chemistry, we refer to that phase change from a liquid phase to a gas phase as vaporization. If I'm going in the opposite direction, from a gas to a liquid, this is condensation. So the rate of vaporization would be how fast I'm going in from a liquid to a gas. So temperature will affect rate of vaporization. If I heat water before it starts that rolling boil, I'm actually increasing that rate of vaporization because I'm adding more thermal energy into those water molecules. They're starting to move around more, and they'll be able to break the surface of the water and move into the gas phase. So I'm increasing that rate of vaporization. If I go from a gas to a liquid, that would be my rate of condensation. So when we look at vapor pressure, we have this dynamic happening here. So we have rate of vaporization, liquid going to a gas, rate of condensation, gas going to a liquid. Before we start that, let's just talk about the 4 types of colligative properties that we're going to study in this chapter. The first one is vapor pressure. The second one is freezing point. The third one is boiling point. This is the temperature at which the solution is going to change states. And then the fourth one is osmotic pressure. So this is a pressure here. So we're going to look at 2 pressures and 2 temperature changes. And so these are going to be the 4 types of colligative properties that we're going to study in this chapter. So we're going to start with vapor pressure. Before we kind of define that, let's just think about what's happening in a solution. So if I have a beaker of water, just pure water, and I set that out on the counter, and since I'm a science nerd, I might have a beaker at my house, so maybe I would set this out on my counter in my kitchen. And over time, what's going to happen is I'm going to have water molecules that are in the liquid. So let's say this is just pure H2O. And I set it out for 3 days. What I'm going to see is my volume of water is going to go down over those 3-day period, because water that's in the liquid phase is going to escape and move into the gas phase over time. So this is just going to happen spontaneously over time as that water sits out on the counter. And then if this is open to the atmosphere, then this water molecule is just going to disperse into the atmosphere in the room. So water molecule will move from the liquid phase to the gas phase. It'll vaporize. And then if this is open, this water molecule is just going to disperse into the rest of the room. If I were to somehow put a lid on this container and I leave it sitting out on my counter, what I'm going to see is that there's not going to be a change in the liquid. The liquid volume isn't going to change because as things move to the gas phase, then they turn around and they move back into the liquid phase. And so I have this equilibrium. So I won't see a change in the volume of the liquid. But that doesn't mean that this isn't happening. So this is still happening. I have water still moving to the gas phase, but since I have it closed off, then as I build up water molecules in the gas phase, they're going to condense back down into the liquid phase. And so this would be a dynamic equilibrium where my rate of vaporization is going to equal the rate of condensation. At this point, if I were to take the vapor pressure, so let's say my pressure here would be vapor pressure is going to equal the pressure of water molecules that are in the gas phase above the liquid. So my vapor pressure would be, what is the pressure of the gas molecules that are water molecules that are here above the surface of this liquid? And so if I'm at dynamic equilibrium, then the vapor pressure of the water is going to equal the vapor pressure of pure water at a particular temperature. If I have this lid closed and it's contained, and I were to measure the vapor pressure of water molecules above this liquid, it would equal the vapor pressure of pure water at whatever temperature I'm at. That would be from a table. So I would look this up in a table. So that is a standardized value. So it would be at some particular temperature. So as long as this was contained, I didn't have anything other than water in here, then I would know what the vapor pressure of water is above this liquid because I could just look it up in a table. But what if this was open to the atmosphere, and what if I had a solute in here? So now I have not pure water, but I have a solution of water. So let's say what happens when I add solute. So I'm going to take the lid off of this guy. Now I'm going to have a solution. I'm going to have water in here still, but now I'm going to add in glucose. So I don't have this pure scenario anymore. I'm going to add glucose to my water to make a solution. And I want to look at how is this going to change the vapor pressure. And I'm looking at the vapor pressure of water because glucose is a solid and it's not going to contribute to the vapor pressure. So I'm going to add glucose to this. And so glucose I'm just going to represent as G. So I'm going to start adding some glucose molecules in here. Glucose is a polar molecule. It's C6H12O6 and it's going to form hydrogen bonding intermolecular forces with water. Add glucose in, it's going to go into solution, it's going to form these intermolecular forces with water, hydrogen bonding. So if I'm looking at the vapor pressure of the water molecules that are above the liquid, so I want to measure the vapor pressure, what's happening here above the liquid. How is adding glucose going to change this vapor pressure? Is it going to keep it the same? Is it going to increase it, or is it going to decrease it? If we think about when we form a solution, so if I add glucose into this and I form a solution of glucose in water, glucose is going to solvate in water because it's going to form intermolecular forces with water that might be stronger than the intermolecular forces between the water molecules. And so by adding glucose in, what I'm going to do is I'm going to lower the vapor pressure of the solution. And glucose does this because it does two things. So this is this is an important point. And it does this because of two reasons. One, it basically I can have glucose molecules that are at the surface of the water where I would normally just have water molecules there. It can hinder H2O liquid to gas by blocking the surface. So I can have these big glucose molecules, they're sitting on the surface right here at the interface, which is where the water molecules need to get to in order to move to the gas phase, because water molecule that's down here in the bottom of the beaker is not going to move to the gas phase. First it has to move to the surface, and then it has to get enough energy to kind of move from the surface to the gas phase. And so if I have, as I increase the number of glucose molecules, I'm going to just statistically increase the number of glucose molecules that are going to be up here closer to the surface. And so that's just sterically going to hinder the water from getting to the gas phase. So that would be one reason. The second reason has to do with intermolecular forces. The glucose is going to form hydrogen bonding, so an intermolecular force with water, and that's going to keep that water in solution. And so it's going to form a stronger intermolecular force than water-water intermolecular forces. And so that's going to actually hinder the water from moving to the gas phase. And so both of these are going to end up lowering the vapor pressure. One, there's just a steric hindrance at the surface, and two, you're forming stronger intermolecular forces that are holding those water in solution. So when I add a solute to a solvent and I want to look at what does that look like above the solution, what is the vapor pressure of that solvent above the solution once I've added in a solute, I'm going to expect it to lower the vapor pressure of that solution. This is Raoult's law. So Raoult's law looks like this. P of solution. So we're looking at vapor pressure, right? So I'm going to have a pressure component here. The pressure of the solution, this is my vapor pressure, is equal to the mole fraction of solvent times the pure vapor pressure of solvent. So let's define these terms here. So this would be my vapor pressure specifically of the solvent above the solution. This is the mole fraction of solvent. So I don't care about the mole fraction of solute because the solvent is what's going into the gas phase. And so as my mole fraction, as the number of moles of solvent to solute go down, then the less number of solvent molecules are going to move from the gas to the liquid phase. And then this term here is a tabulated value of pure solvent vapor pressure at a defined temperature. That's what this little knot means here, is that this is a defined temperature. So a defined set of values. So whenever you see this little knot, when we talked about it in thermochemistry, where we said, okay, this defines a set of standard conditions, the same applies here, because this is going to be a tabulated value. So when I look this up, I'm going to look it up and it's going to give me, okay, this is the value of water at this particular temperature. This would be the vapor pressure of pure water. And so when I plug it into this equation, what it does is if I have pure solvent, I have no solute in there, then this is 1 and these two equal each other. But as I start to add in more and more solute, my mole fraction of solvent is going to go down. Because remember, X of my solvent is number of moles of solvent over total moles of solution. So X of solvent equals 1 if no solute. At that point, then P solution equals 1 times P solvent. And so those essentially equal each other. But as I start to add a solute, X of solvent is going to be less than 1 once solute is added, which means your P solution then is going to be less than your P of solvent. So your vapor pressure of that solvent is going to be less than that pure solvent. And so this is vapor pressure lowering as a result of solute added. And what you notice here is the only time I'm taking into account the solute is when I calculate my mole fraction of my solvent. And so that that's what we mean by a colligative property, is it doesn't matter what the solute is, it only matters that it's reducing the mole fraction of the solvent. So the more solute I add, the lower this value becomes, because the less percentage of moles of solvent over total moles of solution are going to become. And so all that's going to do is drive the vapor pressure down. So that's why vapor pressure is a colligative property. So when I add glucose to water, I'm decreasing the mole fraction of water molecules because I'm increasing glucose, I'm adding glucose in, I'm increasing the number of solute molecules, so this value is going up, this is staying the same, and so this is going to go down. So Raoult's law it allows us to predict the vapor pressure. So I'm going to use this guy here to predict the vapor pressure of the solvent above a solution. So that's what I'm going to use Raoult's law for. What is my vapor pressure of water now that I've added a solute to it? I know what it would be if I just had pure solvent in there, but now I want to know, once I've created a solution, now I have a solute in there, how much lower is this vapor pressure of the solution going to go down? So Raoult's law is really good if you have an ideal solution. So there's some areas where Raoult's law cannot be used. So Raoult's law is not always predictive. And let's think about this. Let's look at some scenarios here. So I'm going to give you 3 scenarios to consider. The first one is, let's say that when I add my solute into solution, my delta H of my solution is essentially 0. So remember, where is delta H coming from? So delta H of 0 means that there's no change, no difference in IMFs between the solvent, delta H of solvent, and delta H of mixture. So there's no significant difference in intermolecular forces there. So that means that the intermolecular forces that are happening between the solvent molecules, any intermolecular forces that would be happening between the solute-solvent intermolecular forces, are pretty much the same. In this case, Raoult's law is predictive. We'll predict the vapor pressure of that solution. So I can use Raoult's law here. If I have no difference in intermolecular forces between the solvent and solvent, right? This is solvent, solvent, and this is solute, solvent, meaning that it's going to behave very similarly. The solute is going to affect the vapor pressure those 2 ways, where it's going to sterically hinder the water molecules or the solvent molecules from moving to the gas phase, and it's going to appreciably keep the solvent molecules in solution because of the intermolecular forces that are being formed. Okay, so that's scenario number 1. Scenario number 2 is that my intermolecular forces between my solute, solvent is greater than my solvent, solvent. Right, so now my delta H of mix is greater than my delta H of my solvent. So that means that once I form that solution, then if my delta H of my mix is greater than the delta H of my solvent, then let's say glucose here has that scenario, then it's going to hold these water molecules into solution. And so I can and so then that's going to allow me to predict, using Raoult's law, that the vapor pressure of the system is going to be lower, right? So I have this scenario here. I've gone into solution because when I form these intermolecular forces between the solvent and the solute, that's going to be greater than the solvent-solvent intermolecular forces. And so that's going to be favored. That means my enthalpy is negative. And that is going to allow me to use Raoult's law to predict. So this is also, Raoult's law will predict the VP of solution. So in both of these cases, my vapor pressure is going to go down, and it's going to go down predictive, and I can use this equation here to figure it out. All I need to know is my mole fraction of solvent, the temperature, and I can look up what my tabulated value of the vapor pressure of the pure solvent would be. My third scenario is the opposite. So let's say that my IMFs between my solute solvent are less than my solvent, right? So now my delta H mix is less than my delta H of my solvent. Right now, what happens is because this is less, the intermolecular force here between the solute molecules and the solvent molecules is less, then that means it's actually going to allow more solvent molecules to move into the gas phase than what you would predict. And so in this instance, Raoult's law is not predictive, cannot use it, because the solute will allow more solvent molecules to move into the gas phase, right? Because by adding your solute, you're basically displacing this intermolecular force here. So when I add in my solute, now I form this intermolecular force here between solute and solvent. If that's less than this intermolecular force, now it's going to be easier for those solvent molecules to move from the liquid to the gas phase. And now in that case, Raoult's law is not going to be predictive because I'm not going to see as great of a decrease in vapor pressure than what I would expect. So my vapor pressure will not lower as much, and it might actually increase. So this is going to be a scenario where Raoult's law is not going to be predictive. All right, one more scenario that can happen here. So this is all we've been dealing with, sort of adding a solid solute to your solution. What if I add a volatile solute? So we'll call this another exception. We'll call this another scenario here. What if I add a volatile solute? And remember, a volatile means that this is a solute that is also capable of moving from liquid to gas in that solution. Because our assumption here with these three is that my solute is non-volatile because it's not going to move into the gas phase. So the only pressure that's above that liquid is being driven by the solute only. So if I add in glucose here, glucose is not moving to the gas phase, it's staying here in solution, and so it's a non-volatile solute because it can't go from the liquid to the gas phase spontaneously just sitting out on the counter, right? The only thing that's going to be in the gas that's coming from this solution is water. But what happens if I have two things, and let's say my solute is volatile, meaning that it can move from the liquid to the gas phase in addition to the solvent? And something like this would be like your alcohols, so methanol, ethanol. So let's say I have methanol. So let's say my solute is going to be methanol, which has a low boiling point and can vaporize as well as water, and probably even better. So now I have my flask here, or my beaker, and my solvent here is water, but now my solute is methanol. And methanol is going to form these intermolecular forces with water here. And above my liquid, I'm going to have water molecules. That would be my vapor pressure of water. But I'm also going to have methanol, because methanol can move from the liquid to the gas phase as well as water moving from the liquid to the gas phase. So now my vapor pressure up here is both my solvent and my solute, whereas before we only considered it as being the solvent because the solute wasn't able to vaporize. And so if I have a volatile solute, now I have to consider both scenarios. So I'm going to apply Raoult's law to both the solute and the solvent, and then I'm going to add my vapor pressure of each together to give the total vapor pressure. So I'm going to have to consider methanol. I'm going to consider methanol by itself. I'm going to consider water by itself. Then I'm going to add both of those vapor pressures together, and that should give me the total pressure here. Because remember, Dalton's law of partial pressure, the total pressure of a system is equal to the pressures of the internal components of that system. So in this case, it would be the partial pressure of water plus the partial pressure of methanol. So what is the pressure of these gases here above? So this would be my total vapor pressure. And now I have to consider both the solvent and the solute. This is the vapor pressure of water, and this is the vapor pressure of methanol. So I'm going to calculate these separately, and then as my second step, I'm going to add them together, and that's going to give me my total vapor pressure. So this is a scenario where I'm going to use Rations Law twice, right? So I'm going to calculate the vapor pressure of water by looking at the mole fraction of water and the pure vapor pressure of water. And then I'm also going to do the same thing to methanol by looking at the mole fraction of methanol and the pure vapor pressure of methanol, because this is volatile, so I'm going to be able to find this value in a table. So any volatile liquid is going to have a vapor pressure value. And so I'm going to calculate both of these independently, then I'm going to put them into this equation and get my overall vapor pressure. So in this case, both solvent and solute contribute to the vapor pressure. And they may not contribute equally, it depends on how much of them are there, but they are both going to contribute to the vapor pressure of that solution. So I'm going to go to and show you a slide really quickly. And if you think back to chapter 11, where we had those phase diagrams where you looked at the change in states of matter, solid, liquid, gas, based on pressure and temperature, right? If I look at vapor pressure, because it's a colligative property, once I form a solution, what that's going to do is that's going to lower the vapor pressure of that solution. It's going to move it from where this blue line is here to the red line, because now I have less of that solvent that is able to move to the gas phase. I'm adding in solute and I'm reducing that mole fraction. So what I see here is this vapor pressure lowering. So if I were to apply it to that phase diagram from chapter 11, this is what it would look like, which means that my melting point and my boiling point of my solvent would be here, and then the solution is going to change. And so we'll come back to the melting point and boiling point when we get into our part 4 of this chapter. Okay, so this is where we're going to end for right now. We will be doing lots of calculations on Raoult's law and looking at vapor pressure when we come together in our Zoom session.